We're going to look here at Green's theorem, which is section 16.4. And what Green's theorem is a tool for helping us to calculate the work integral in certain situations. So here's a warm-up problem. Suppose we were asked to compute this. Now remember, this is differential form. It's the same as when we were asked to compute the integral of f dot dr. So if you prefer vector notation, you can do it like that. I just like to give you both versions so you recognize what it is. C consists of the arc of the parabola from 0, 0 to 1, 1. So like so. Followed by the line segments from 1, 1 to 0, 1. So then we have this piece here. And then 0, 1 to 0, 0. So that is a piecewise smooth curve. We're going to have 3 separate pieces there. And so to compute that directly, well, first of all, I guess it would be really smart if we checked to see whether our vector field was conservative, because if it is, you have a closed path, conservative, the answer would be 0. We'd be done. So to see whether or not it's conservative, we take the y component, take the partial with respect to x. So we're going to take the partial with respect to x of xy, and we're going to take the partial with respect to y of the x component, x squared, y squared. So this with respect to x, that's with respect to y. That's what I'm doing here. And we want to know whether or not these are equal. The partial here with respect to x would be y, and the partial here with respect to y would be 2x squared y. So those are not equal. So then this vector field is not conservative. So that means we're actually going to need to compute the integral. And this is a piecewise smooth curve. So we have curve 1, curve 2, curve 3. So what we're going to need to do to find the work around the whole curve is to break it up into each of the pieces. I'll just use shorthand notation here. So we're going to need to do each piece. So C1, parameterize x equals t, y equals t squared. T goes from 0 to 1 because x goes from 0 to 1. T goes from 0 to 1. And so x squared y squared dx, I'm just rewriting the problem, plus x y dy is going to become, we're putting in x equals t here, we're putting y equals t squared here. So t squared squared, that's t to the 4th, and t squared, so t to the 6th. dx is dx dt, so 1 dt, so 1 dt, plus xy dy, xy is t times t squared, so t cubed, and then my dy is dy dt, dt, so dy dt is 2t, dt. So 0 to 1. So this is going to be t to the 6th integrated is 1/7 t to the 7. This is going to be 2t to the 4th, so that's going to be, after I integrate it, 2t to the 5th over 5, 0 to 1. So 1/7 plus 2/5 is 19 over 35. So that's the first one. Okay, then we have C2. C2 goes from 1, 1 to 0, 0. So parameterizing, I get x and y. My initial point is 1 and 1. And, whoops, this is 0, 1 here. And the vector here, 0 minus 1 is negative 1. 1 minus 1 is 0. That's 0 to 1 for that line segment. So putting into our integral, we have x squared, y squared. So that's 1 minus t squared, 1 squared. So 1 minus t squared. Dx is dx dt dt, so that's going to give me a factor of negative 1. And then xy, 1 minus t times 1. Then dy is dy dt dt, that's 0. So that's times 0 dt from 0 to 1. And so that is going to be negative 1, 0 to 1, 1 minus t squared dt. I'll let you do the computation here, but you're going to end up with negative 1/3. So the last one, C3, from 0, 1 to 0, 0. Parameterizing that, I get 0, 1, and the direction vector, t goes from 0 to 1. Into the integral, x squared, y squared, that's going to be a 0. xy, that's going to be a 0. So that is 0, so 0. And so that means that our answer up here, the integral for C1 is here, and for C2 is here, and for C3 here. And so we end up with 22/105. Okay, so that's just a review, working with the piecewise smooth curve. When f is not conservative, the only technique we have is to do it directly. But then we have Green's theorem. And Green's theorem is going to be a tool that we can use even if f is not conservative, but there's a catch. So let C be a positively oriented, piecewise smooth, simple closed curve in the xy plane. I'll come back to that. If P and Q have continuous partials in an open region that contains D, then this integral, now remember that's just the differential form of the integral if you like to see it better this way. This is our work integral. Here's what it's saying is to do this integral, it's a double integral of this mixed partial thing. These were what we were testing to see if they were equal, to see whether or not I had a conservative vector field. So let me read this again. C is a positively oriented, piecewise smooth, simple closed curve in the plane. Okay, so we have some sort of closed curve in the plane. Positively oriented means counterclockwise. Now, when the curves start getting more complicated, if counterclockwise seems confusing, the other way positively oriented is described is that if you were walking along the curve, the enclosed region is on your left. Okay, so that's positively oriented. Piecewise smooth just means it doesn't have to be all one continuous smooth curve. It can be in pieces like this. Simple closed curve. Simple means that it's not intersecting itself. And D is the region bound by C. So D is the region bound by C. What it means is that it is a two-dimensional region, not just the curve, but a whole plane region. So here's what Green's theorem is saying. It's saying that if P and Q have continuous partial derivatives, that if I want to compute the work done around this curve, I can do that by computing the double integral of this function. Okay, the double integral of this function. So we're going to learn a little more why this works when we get to section 16.8. But it's interesting to note that if we want to know something about what's happening on the boundary, it's related to what's happening inside. Fundamental theorem of calculus kind of says the same thing. When we want to evaluate an integral, we really are looking only at what's happening on the endpoints. We're looking at what's happening on the edge to figure out a relationship inside. Okay, so I'm mostly just showing us how to use this, not going into the theory. Some of the proof you could understand right now. Some of it is pretty straightforward, but it gets more complicated, and it can also apply to more complicated regions. So those of you going on in math and engineering, you'll find that even if your domain was something that wasn't just a simple closed curve, but there was a hole in the middle, then you can still apply Green's theorem. You're just going to have to get a little creative about breaking it apart into two separate curves, like so, and then another one that goes over here, and so on. So we're not going to go into all that. I'm going to leave that for your advanced calculus or your engineering mathematics classes. I just want to take a look at the basics of Green's theorem. So here's what it says in context of this problem. This problem, we do have counterclockwise. So our curve is oriented in the correct direction there. And so our D that is talked about in the theorem is this region that's enclosed. And so according to Green's theorem, if we wanted to compute this integral, this work integral, that just happens to be given in differential form, I can compute the double integral of partial x qx py. Remember, pq. So qx py. Y's component with respect to x minus x's component with respect to y. And that's what I have done when I've done the switching of orders. I should have done a better job here. Remember, when we check for conservative, I tell you, let's take partial with respect to x here. Let's take partial with respect to y here. They are not equal, so it's not conservative. But now what Green's theorem is telling us is take those and subtract them. Okay, so that's why I do that crisscrossing thing. You don't have to do that, but in the case where f is not conservative and these two don't equal each other, if the curve is closed, so that's the part I should have really underlined. If the curve is closed, then subtracting this becomes our integral, and we can now do this as a double integral. Okay. Now, as I said, I don't really like to just put theorems up here without really going into depth, but this is just all introductory here. So if I'm going to integrate this, I can either go dy dx or dx dy, doesn't matter. That's an x squared, so I might prefer to go y first, but either way. So y goes from curve to curve. That would be y equals x squared to y equals 1. And x goes from 0 to 1. So that's an easy integral. I am going to go ahead and do it just because I don't have the answer for this written down. I want to check. So I should get the same thing here as I did there. And if I didn't, then I'm going to have to find my mistake. Okay, so I'm integrating with respect to y. So I'm going to get 1/2 y squared minus x squared y squared. Y goes from x squared to 1. So putting in 1, I get 1/2 minus x squared. Subtract what I get when I put in the x squared for y. And that's going to be 1/2 x to the 4th minus x to the 6th dx, right? Putting in 1, I get 1/2 minus x squared. Putting in x squared, I get x squared squared, so x to the 4th, minus putting in x squared, I get x to the 4th and x squared, that's x to the 6th. And so, what have we got? 1/2 minus x squared minus 1/2 x to the 4th plus x to the 6th. And so that's going to be 1/2 x minus x cubed over 3 minus x to the 5th over 10 plus x to the 7th over 7. Something tells me we might get something different here. Whoops, yes, from 0 to 1. So 1/2 minus 1/3 minus 1/10 plus 1/7. So this turns out to be 22 over 105, which matches, as it should, what we got up here. Okay, so Green's theorem. Green's theorem gives us another way of computing line, line integrals if our curve is closed and if it's oriented positively. Now, if the curve that we were given is oriented the other way, that's fine. Then we can apply Green's theorem to the one that's positively oriented, and our answer will be exactly the opposite of that, because when we go on a path, same path, but the other direction, our work is negative of what it was, the other direction. Okay, so one more quick example here. Find the work done by the vector field and moving a particle along the piecewise smooth curve shown. Now, it didn't show very well, but this was cosine of x. We go that way and then come back along here. So we'll start here, we go around. So first thing I would do is I would see if this is conservative. This is a closed path. So if the vector field is conservative, I get 0, I'm done. So I take the partial here with respect to x, and I get 2x, and I take the partial here with respect to y, and we get 2y. So no, they're not equal. F is not conservative. So once we get that f is not conservative, we only have two tools. Two ways to do this. We could do this directly, or if closed, we can use Green's theorem. Okay, so this is closed, so we can use Green's theorem. The only problem is that this is oriented not counterclockwise. This is oriented in the opposite direction. And so let's let minus c be this curve, this closed curve in the opposite direction to the one that we were given. And notice that the curve minus c is positively oriented, so we can apply Green's theorem to minus c. Okay, and then our answer will be the opposite of that. Okay, so Green's theorem would say that if I wanted to compute the work around minus c, okay, the other direction, not the one that we want, that's going to be the double integral of partial of qx minus py. I actually forget those letters, which one's q and which one's p, but I remember it this way. This with respect to x, this with respect to y, so 2x minus 2y. 2x minus 2y. Okay, this is our D in here, this whole enclosed region. So that makes the most sense, dy dx. Y goes from 0 to cosine of x, as x goes from negative pi over 2 to pi over 2. So we can do it that way. If we did it directly, we would have to break it down into two piecewise smooth curves. So you can try that and check that we get the same answer. So if I'm integrating with respect to y, I get 2xy minus y squared, going from 0 to cosine of x. I'm evaluating at y. So that's 2x cosine of x minus cosine squared of x, subtracting what we get when we put in 0, which is 0. Okay, now notice you've got negative a to a. Anytime I see that, I look for a shortcut, which is if either of these pieces are odd, then that integral will be 0. That part of the integral is 0. So it turns out this is odd, so that integral will be 0. So that just saves me a little bit. If you didn't see that, that's fine. You would integrate that by parts. So I have negative pi over 2 to pi over 2 minus cosine squared of x dx. Now you can also use that fact, negative a to a of an odd function is 0. There's the other version of that fact that is negative a to a of an even function, and this is an even function. We can just go from 0 to pi over 2 and double it if you want. Just means that we're not going to have to evaluate the integrand, the antiderivative at negative pi over 2. We need to go 0 instead. So cosine squared is 1/2 x plus 1/4 sine of 2x. Either you remember that or you use the power reducing formula. Putting in pi over 2, I get negative 2 times pi over 4. Put pi over 2 here, I get sine of pi is 0. Subtract what I get when I put in 0, which is 0. And so I get negative pi over 2. Okay, now we have to remember though, that is for the opposite direction of what we want. So then the one that we want is the opposite of this one, because we're going in the other direction. And so that's going to be minus, this one here is the one that we just did with Green's theorem. So that's minus a minus pi over 2. And so we get pi over 2. All right. It's easy to forget to change that sign at the end. So as soon as I recognize that we're going in the wrong direction, I would typically write this part right here. This equals minus this equals, and then leave it blank until I come up with that. But otherwise, it's so easy to forget to change the sign.